Hello, you're welcome. Okay, so now we are gonna be discussing wave, okay, in physics. Okay, so I will start with the definition of a wave, right? Now, a wave is defined as a disturbance that travels from one part of a medium to the other, transferring energy with the average position of the particles of the medium remaining constant. Okay, so which by conclusion, I can simply say that a wave actually transfers energy. Okay, what wave does is that it transfers energy, and of course the energy it transfers is from one part of the medium to the other, right? So please take note of that, right? The medium, the particles, the average position of the particles of the medium is constant, all right? But from the part where that disturbance is actually being generated, energy is being transferred. For example, let's say you got a trough of water, okay, all right, that has water inside of it, and of course the water is just uh, horizontal. Let me just use, okay, it's not disturbed. Okay, there's no ripple, the water doesn't have any ripple. Now you now create, actually touch one part of the water, the inside the trough. Okay, you now discover that ripple will be generated, and that ripple moves, okay, in form of a wave. And of course, from the point where it is being generated, it will move from that part to the other part of the medium, and it transfers energy. So this ripples is like energy that actually moves from one part of a medium to the other. So a wave is a disturbance that travels from one part of a medium to the other, transferring energy with the average position of the medium. Then of course the medium is a, which being the trough of water being filled with water, is still the same. There is no translation. Of course, it's still the average position is still gonna be constant. All right, so please take note of that. All right, so that is the definition of a wave. So now we're going to be looking at the graph, okay, of a wave. Wave can be described also using a graph. You can draw a graph of a wave, okay. So it's a graph that actually describes the displacement or the oscillation of the wave with time. All right, so this is the vertical axis, and of course this is the horizontal axis. So we are talking about the graph, okay, that illustrates a wave. So now this is the vertical axis and this horizontal axis, okay. All right, so now once a wave starts, you're gonna see something like this. This is how you draw the graph, okay. um it's a periodic motion, it repeats itself, okay. It repeats itself with time. All right, so now this horizontal as it represent the time. Of course, this vertical is actually the displacement. Now the maximum displacement of this wave at this point is the maximum displacement, that is the minimum, okay. The maximum displacement of this wave is what is regarded as the crest of the wave. This is the crest, okay, while the minimum is the trough of the wave. This point is the trough of the wave. Okay, let's just say the maximum point at the maximum displacement. Okay, this point is a point, all right, not a distance, it's a point. Okay, so the maximum point and the minimum point of the wave is the crest and the trough respectively. So please take note of that. All right, so now we are going to look at the terms that is used in describing a wave. Every topic in physics has terms that describe, okay, the basic concept of that particular topic. So that's what we're going to be looking at. Okay, so I clean up the screen, and of course I'll be taking some notes which i'll be I'll be pasting on the screen, so that I'll be discussing it, and of course you will be seeing it. All right, so now let's go to the terms that is used in describing a wave. So we're going to discuss these terms, and of course you should take note of them. Here we go. So now I have it here. All right, the terms used in describing a wave. So we are starting with amplitude. Every wave has amplitude, and of course A is the symbol used, okay, symbol used for amplitude, right? So what is the amplitude of a wave? This is the distance between the mean position of the wave, okay, of course the mean position, that where the wave is starting, okay, the starting point of the wave, okay, and the maximum displacement of the wave. Let me describe that within a graph. So let's say this is, I have my wave, okay. it starts from here, goes up, and of course, so it has displacement up and down. So the distance from this point to this maximum displacement is what is known as amplitude. It's still the same distance from here to this minimum point is the amplitude of the wave. So please take note. Since it's a distance, it's measured in meters. All right. So please take note of that amplitude represented by A. Then the next term we need to talk about is the wavelength of a wave, represented by the symbol lambda. This symbol is called lambda. What's the wavelength of a wave? This is the horizontal distance traveled by the wave, okay, as it actually completes one circle. Okay, when I measure the horizontal distance the wave moves, okay, as it completes one circle, then that is what is regarded as wavelength. Is measured in meters. Let me actually illustrate that. Okay, so let's say I got a wave. All right, draw my graph. I will describe all this with a graph. Right, here we go. All right, so this wave moves. This is half circle. These are not half circle. All right, half circle plus half circle is full circle. So the distance from this point to the point where this wave completes this circle is one wavelength. So it simply means that now if I should go further and draw more, okay, so you discover that this is one wavelength. From here to here is another one wavelength. All right, then from here this is half wavelength. So the total wavelength of this wave is 2.5 wavelength. That's the total wavelength of this wave. Okay, so please take note of that. All right, so here we go. Now we are going to be talking about a period of a wave. All these terms are very important, represented by the capital letter T. All right, now the period of a wave is the time it takes the wave to complete one circle. Okay, the time you measure in seconds it takes that wave to complete one circle. All right, so which simply means I can simply also say that the period of a wave is the time it takes for this wave to actually complete one wavelength. All right, and we use capital letter T to represent it. Okay, so please take note of that. It's measured in seconds. All right, let's proceed with some other terms. Okay, so we're going to be talking about frequency and of course some other terms in wave. So I'll bring it up to this screen. Here we go. All right, so now what about the frequency of a wave by the symbol F? Now the frequency of a wave is the number of cycles, okay, that wave covers in a given time, in a particular time. In fact, we can simply say the frequency of a wave is talking about the the speed or the oscillation, how fast, or okay, the rate of the oscillation of the wave, how fast the wave oscillates with time. All right, so that means a wave that actually covers more cycle in a little time has a very high frequency. So that is why we can simply say that, okay, frequency of the wave F is the number of cycle it covers and per unit time. All right, good. So if the number of cycle we are considering is just one cycle, okay, that's one, and the time it takes for a wave to complete one cycle, already we talked about that, it is the period, which is capital letter T. So we can simply say that period can be number of cycles completed per unit time n all over T, or F, period is so the reciprocal of the frequency is the reciprocal of the period. Okay, this and this, all right, represent frequency of a wave. For example, let's illustrate some let's illustrate this using a question example. Okay, let's say you got a graph. Okay, I'm gonna draw a graph again. Then of course, let's say you have this wave moving this way. Okay, so yes, okay, so let's say at this point you have 2 seconds. At this point you have 2 seconds. At this point you have, sorry, let's say 4 seconds. And at this point, okay, So we simply mean that if this is 2 seconds, right? This is 3 seconds, this is 4. Okay, this is 5, and this is 6, if I'm not mistaken, right? Yeah, I'm not mistaken, right? 6. So if you are being asked what is the period of this wave, all right, what is the frequency of this wave? The frequency is equal to the number of oscillation per unit time, per time. How many oscillations can we count here? 1 oscillation, 2 oscillation, then 3 oscillation. Okay, so that's gonna be 3 oscillation, then divided by the time. The time for this 3 oscillation to complete is 6. Okay, so this is just, I'm just giving you a typical example of how you can evaluate a period. Okay, so from this particular graph, okay, we can also conclude that the period of this wave is 2 seconds. Of course, capital that is 2 seconds. As you can see here, the time it takes for this wave to actually complete 1 second is 2 seconds. All right, 2 seconds. So please take note. So these terms are really very important. In fact, if you understand this basic concept, you will not find it very difficult with any question, okay, that has to do with wave. All right, so these are the basic concepts you need to understand. So let's proceed. That is the period, the frequency of a wave. All right, so now we are going to talk about another important term, concept known as the phase difference or the phase angle of a wave. Okay, all right, now you know very well that if we said that a wave can be illustrated using a graph, right? Which of course I'm very sure that you must have drawn one. Now you discover that some graph you draw, okay, some graph can start from the origin, some graph may not start from the origin. Are you okay? So graph, depending on where this graph starts, the same thing happen with wave. Some wave you draw can start from the origin, like the wave we have here starts from the origin, while some may not start from the origin. Okay, so the wave that doesn't start from the origin have an angle, that means it's lagging. Okay, normally if there's a rotation, let's say rotation start from 0 and they start rotating, but some doesn't start from 0, right? So now that now brings us to the definition of phase difference. So now the phase difference of phase angle of a wave, okay, is the angular difference measured in radians between a wave that starts from the origin and the one that does not. Okay, so any wave that starts from the origin have phase angle of 0. It doesn't have any phase angle, okay, because it's starting from the origin. Okay, now that simply means that if for me to illustrate that, let me still draw my graph. Okay, I draw my graph. If I have something like this, all right, and of course this is my wave. Please pardon my just for illustration. Okay, this wave, the phase angle of this wave is 0 degrees. Start from 0 degrees, so it doesn't have any phase. But a situation where this wave now is started from this point, from here to here. Okay, remember this is 90 degrees. How do I know? Okay, you know that this point this is half circle. All right, this is half circle. Full circle is 360 degrees. Okay, if full circle is 360 degrees, then half circle at this point, this point here is half circle, that's 180 degrees. So this is half of half circle, that's 90 degrees. So let's say a situation now where this I'm just shift this wave now. It started from this point. Okay, you discover that I shift it. Yeah, here we go. So now you can now start. You discover that this is where this wave started at 90 degrees. Okay, so I can simply say the phase angle of this wave is 90 degrees. Okay, but that's the difference between it and the one that starts from 0. Okay, and of course, unfortunately, in wave or circular motion generally, we don't use degrees to represent angle, okay, angular distance, but rather we use radians. So the question is, how do you convert radius from degrees to radians? It's just very simple. Okay, 360 degrees, which of course is a full circle, right? 360 degrees is equal to 2 pi radians. 2 pi rad. So if that is the case, half of 360, that's 180. So if this wave is 180 degrees, that means in radius is pi radians, pi rad. Okay, so I hope you are getting it. Then of course, if it is 90 degrees, like the one we have there, that is half of 180, right? So that's pi all over 2. Pi all over 2 rad. All right, so I hope that is well understood. That is the phase angle. Please take note of them, go through it. Okay, one thing you should know about science generally. Okay, um, if you want to be efficient, okay, if you want to be good uh, in this subject, okay, you have to devise a means to which you understand the concept instead of cramming it. If you understand the concept, definitely you can actually put it in your own ways. Okay, so understand the concept, don't cram. All right, so we go to the next time, okay, which of course is the wave velocity. Now, the wave velocity is the rate at which a wave antenna is in this, right? The rate at which the wave changes displacement. Okay, please, the rate at which the wave changes is horizontal displacement. Because there are different displacement. We have both vertical displacement and horizontal displacement. Okay, all right, horizontal displacement. Okay, horizontal distance. All right. So the rate at which the wave actually remember, a wave vibrates at the same time. It can also move from one part of the medium to another. There are two movements that a wave has. Okay, let me just bring that to your notice. I'm using, let's say I want to illustrate using the water repo. Okay, this is the water. Okay, this is where I disturb the wave. So where I disturb the wave, you discover that it will vibrate up and down at the same time. Yes, it travels. So a wave travels, are you okay, horizontally, and of course vibrates. Okay, so up, down, as you can see here. All right, so the velocity we're looking at is talking about, okay, the horizontal distance. Okay, it travel, the rate at which it changes to horizontal distance, which simply means that I can simply say that, okay, wave velocity v is the rate of change of horizontal distance, or we know that for one circle the horizontal distance is one wavelength. Are you okay? For one circle, the horizontal distance is one wavelength, and the time for that one circle, okay, to complete is, of course, it's a period. I already talked about that. The time for one circle is a period. The distance for one circle, okay, the horizontal distance for one circle is wavelength. All right. So I want to show, this is the formula of velocity. I want to prove how this formula came about. Right. So velocity is always given as wavelength multiplied by frequency. I want to prove that. All right. So how do we do this? All right. So it simply means that this is, of course, a fraction. I can split it. And of course, already I've told you already that frequency is also given as the reciprocal of a period, of course. So that actually changes. So please take note of this formula. Velocity of a wave is given as the wavelength multiplied by the frequency. Okay. So I hope that is well understood. I think we're gonna, so let's look at question. I think a question, we need a question to help us illustrate this, right? Here we go. I bring it up to the screen. Here we go. Okay. I paste. Question goes like this. What is the wavelength, okay, of a radio station? Alright? Of a radio station transmitting at a frequency of 20 kilohertz. So this radio station is transmitting at a frequency of 20 kilohertz. And of course, you know that kilo is 1 times 1000. So 20 kilohertz is 20 times 1000. That should be 20,000 hertz, right? 20,000 hertz. All right, here we go. Then, of course, given that the velocity of light, of course, every radio wave, electromagnetic wave, actually travels with the velocity of light, which is constant with the value of 3 times 10 raised to the power of 8. All right, meter per second. Here we go. All right, so now what are we looking for? We are being asked to evaluate the wavelength lambda. So as simple as it is, just is what I look. We use this formula, right? V is equal to lambda f. So of course, lambda from here is going to be equal to v divided by frequency. Okay, so here we go. Of course, that's going to be 3 times 10 raised to the power 8 divided by 2, 20,000. Okay, so this should be 2 times 10 raised to the power 4, right? How many times 4 zeros, right? 10 raised to the power 4. If I do 3 over 2, if I do 3 over 2, I have 1.5. Okay. And of course, for standard forms, for powers of 10, 10 raised to the power 8 divided by 10 raised to the power 4. Okay. Of course, 4 zeros out of this cancels 4 zeros out of from 8. So I have just 4 zeros here. Right. So this is going to be, so what I will have is 10 raised to the power 4, right? So that is 10,000. So you can use your calculator. This is 10,000, right? Use your calculator. You can do 1.5 times 10,000, and of course you have it. So it is wavelength. Please take note. The SI unit of wavelength is meters. So you just have to put that down. All right. So I hope we are on the same page. Let's move forward. So here we're gonna talk about different ways a wave can be classified. Okay. Classification of wave. Please, you need to know this because that is the basic things that might be coming out, okay, in the examination, right? So here we go. Now, wave can be classified. We are talking about classification. All right. Classification of wave. All right, so shall we go? All right, wave can be classified in the following ways. Okay, so a wave can actually be classified as a mechanical wave or an electromagnetic wave. A wave cannot be mechanical and electromagnetic at the same time. So it's either you belong to a mechanical or you belong to the department of electromagnetic. So you need to know the difference between these two. So what's a mechanical wave? All right, that's exactly what we should actually ask ourselves. Now, a mechanical wave is a wave that actually requires material medium. Okay, any wave that needs material medium for its propagation, for its movement, all right, they are called mechanical wave. So without material medium, of course, material medium I'm talking about here is either the wave travel through solid, or it travels through liquid, right, or it travels through a gas. Okay, so it must need this three state of matter for it to move. Example of a mechanical wave, simple example is sound wave. A sound must need this, or this for it to move. In fact, the sound that actually you hear is when someone says something to you through air, okay? The person is not coming to talk to your eardrum, to your ear directly, whisper to you. It talks, okay? And of course, you hear the sound. It's because air actually transfers the sound from the source, okay, to the listener. Air transfers it. So air becomes the medium for the transfer. So please take note of that. Okay, so that's one problem. So why electromagnetic wave does not require no material medium? Electromagnetic wave, a wave that doesn't require material medium for their propagation. Alright. So we simply mean that anytime in physics you hear of when there's no material medium, any medium that doesn't, if there's no material medium, we refer to no material medium as vacuum. Okay, so an electromagnetic wave can only travel in a vacuum. No material, no gas, no liquid. Okay, it doesn't need that. Though it can pass through it, but it doesn't need it for its movement. All right. So, which simply means that we are going to look at the different electromagnetic wave, the example. Okay, now example of electromagnetic wave is just we are going to illustrate it using an acronym, which of course is the acronym here is RELOS G. Acronym that we use to illustrate electromagnetic wave is RELOS G. Okay, R represents radio. These are different electromagnetic wave. Apart all the electromagnetic wave, R represents radio wave. Is okay. The list of them, of course, I represent infrared. L represents light. U represent ultraviolet, ultraviolet, ultraviolet ray. Okay, then of course X represent X-ray, X-ray, and the last but not the least, G represent gamma. Okay, right. So radio, from radio station, infrared mostly from your phone, light of course from your touch, ultraviolet from the sun, X-ray used in scanning, okay, human body, of course, gamma is a radiation, okay, radioactive substance. All right, now one thing about all this acronym, the RELOS G, is that this wave is being arranged according to their increasing frequency. Increasing frequency. So please take note of that. So which simply means that among all this wave, the one that have the highest frequency is gamma ray, okay? Of course, it will have the highest energy. All right, gamma ray, highest frequency. Then of course, if we say that the frequency is increasing downward, okay, the wavelength is vice versa. Why? Because we know from our formula of velocity, okay, velocity is equal to lambda f, of course. If wavelength now is going to be v all over f, okay, this is shows that from this relationship, wavelength is reciprocal frequency. Anytime you see any relationship where one parameter is at the numerator, as you see that the other parameter in that formula is in the denominator, that's how they are connected in the equation, okay? It's called inverse relationship, okay? All right, so it simply means that this is a reciprocal of this. That simply means that when velocity is increasing, where frequency is reducing, okay? So if definitely frequency is increasing this way, right, wavelength increases this way. So radio have the highest wavelength. All right, highest lambda, highest wavelength. I hope that is well understood. Okay, so let's now talk about this, the last but not the least. Okay, the difference between longitudinal and the transverse wave, right? So it's either a wave can be described as longitudinal or it is transverse. It can be both. All right. So what is a transverse wave? A transverse wave is the type of wave in which the vibrating particles, okay, travels in a perpendicular direction with the direction of the movement, with the direction of the propagation of the medium, right? If that actually makes sense. Okay, so let's talk about it. Let's say this is where the medium is moving, okay? And of course, the particle vibrate up and down this perpendicular direction, okay? So particles is vertical, vibrating vertically, while medium is moving horizontally, okay? This is 90 degrees. So when the particles, vibration of the particles is perpendicular with the movement of the medium, we call such wave a transverse wave. And of course, example of transverse wave is all the electromagnetic wave. They are all transverse wave, okay? All the electromagnetic wave. All right? Electromagnetic wave, they are all transverse wave. Because they are simply made up of electric. All right? They are made up of electric, the electric component with the magnetic component, okay, vibrating in a perpendicular direction. All right, so electric, magnetic, perpendicular to each other, okay. So all of them, they are all electromagnetic wave. All right, so please take note of that so you can get. All right, so all of them, they are all transverse wave. Please pardon me. All right, that's transverse wave. While longitudinal wave, okay, both the material medium, both the medium, sorry, the medium of propagation, okay, and of course the vibrating particles, okay, the direction of the wave, the direction of the wave, okay, and the particles, they are the same. All right, particles, medium, they go in the same direction. A typical example of a longitudinal wave, okay, is sound in air. Example, sound, okay, that is transmitted via through air. Now, when sound is being released through air particles transfer the sound by what? Okay, compressing and actually refracting, okay, or spreading. All right, now let's say this is a source of sound, and this is the listener. Right? So if the sound is being released, air carries it, and the air particles actually compress at some point, then it spread out at some point. Okay, compress at some point, spread out. Okay, why it actually carries it in the same direction with the compression and the spread. Okay, so when the particles, vibration of the particles move in the same direction with the movement, okay, of the wave, all right, we call such longitudinal wave. Okay, so please take note. So sound vibration in air is an example of longitudinal wave. So I hope that is well understood. All right, so we are good, I hope. All right, so that is different ways we could actually classify wave. So now let's get to a very important part of this tutorial. Okay, so we're going to be looking at the equation of a progressive wave. Okay, so this part, okay, deals with some calculations. All right, so we'll talk about it. I'll clear up the screens. So let's get started. The equation of a progressive wave. Yeah. Sorry, did I talk about? Okay, there's one I didn't talk about. Please. Progressive and stationary wave. Okay, please. I didn't discuss this one. All right, please pardon me. So, difference between a progressive wave and a stationary wave. So, when is a wave said to be progressive? Okay, let's talk about that. Here we go. Now, a wave is progressive. Okay, let's start with this. A progressive wave, okay, is a wave that is continuous from a source. Okay, once it starts, it moves continuously, and of course, it doesn't reflect back to the medium. Okay, it is it is directional. It is unidirectional. What I mean by unidirectional is you know where it started and of course you know where it's going. Okay, so it's a wave that travels continuously from the source. Okay, without returning back to the medium. Right, so this is a progressive wave. So it goes on and on. There's no backward movement. Right, it's a progressive wave. But a stationary wave is when is actually achieved when you have, okay, a wave reflects or possibly two identical wave. Okay, when you have two identical wave traveling in opposite direction. Okay, and it happens mostly when the wave actually reflects as it encounters, okay, two boundaries. Let's say we have a boundary here. So now I have a wave that goes, okay, with a phase angle 0, right? Okay, so now then I have another wave which of course is going on negative phase angle of 180 degrees. Okay, this is positive, this is a positive, this is negative. So this one comes here, less comes here. Okay, and of course it happens like when this one get to this point, it actually it reflects. Okay, reflects, move in opposite direction, right? So pardon my, so this is exactly what you have, uh okay, for a stationary wave. All right, two identical wave, all right, traveling in opposite direction. So at the point, this point where they actually, their source, where they began, all right, is known as the node of the wave, the node. While the maximum point, okay, the maximum displacement, okay, is what is regarded as the antinode. Okay, let me, the antinode. Okay, so if I can actually illustrate the distance from the node and the antinode, as you can see, okay, antinode is at this point, this is the node, this is antinode, and we know that this is 90 degrees, okay, and of course that is quarter wavelength. So the distance from the node and the antinode is always quarter wavelength, one wavelength divided by 4. Of course that is true. Okay, this is half wavelength and this is quarter wavelength. Okay, one wavelength divided by 4. So please take note of that as we now go to the equation I actually talked about, right? At the equation of a progressive wave. Now we will describe the equation of a progressive wave here. Then of course, excuse me, pardon me, bring that up, right? All right, so we're looking at the equation of a progressive wave. Okay, now why are we talking about equation of a progressive wave? As we already know, all right, we said that a wave, okay, can be represented in a graph, right? A wave have a graph that describe it, okay? And of course, you know very well that every graph has an equation that gives rise to that graph. If you have drawn graph before, there's always an equation, okay, that actually gave rise to the graph. So if graph that you've actually drawn before has an equation, definitely a wave is not an exception. So a wave will always have equation that gave birth to the graph, okay, of the wave, and that's what we're going to be talking about. Okay, so for a progressive wave, the equation of a progressive wave is given as y equal to a sine omega t then minus phi. All right, so this is one way of representing the equation. We'll look at what all this represent. Of course, you know very well that y is, of course, it's always, we use that as our vertical as is horizontal as is x, right? And of course, at this point, that is this position of the wave can be represented as in time interval. Okay, the vibration is based on time, so let's look at what all this represent. All right, we have the a, which of course we know that the a is the amplitude of the wave. All right, so we simply, any number here is the amplitude of the wave. All right, now this symbol known as the omega is what is called the angular frequency of the wave. So angular frequency, now angular frequency is just different from the normal or the linear, okay, frequency. Okay, so we call it angular frequency. Of course, in circular motion we call it angular velocity, but here is in wave we call it angular frequency, right? Please take note of that. And of course, angular frequency is given as 2 pi f, 2 pi, okay, 2 pi f. Please take note of that. All right, why this is phi, we've talked about phi before, is the phase angle, right, of the wave. So we simply mean that this is the, that's for this wave. Now remember, any wave that starts from the origin doesn't have any phase angle. So for this wave, now this wave here is the phase angle is 0. Okay, so this can actually be neglected, so that I can, this equation now can, for this wave, is can be just simply y is equal to a, right, sine omega t. That's all. All right, because the phase angle is 0. Now the phase angle of a wave, okay, is given by kx. That's another way of expressing phase angle. What is k? Of course, s is the horizontal displacement, right? Just like we have on y and s. So now what is k? Remember, a wave travels, right? It vibrates. K is known as wave number. The wave number of a wave. And the wave number of a wave is equal to the number of, okay, angles or oscillation cycle it makes per one wavelength. Okay, so k, the wave number of a wave, is the number of cycle. Remember, 2 pi is one cycle. Okay, the number of cycle that wave makes per one wavelength. All right. Now, describing all those things in details might actually probably bring some complexity. So we're just going to, I'm going to simplify it. So how do I simplify it? I will just take out what I need. Okay. Just lay emphasis on what is really important. What is important is this. Take note of this. This is the first formula for the equation of a wave. Okay. We're going to apply this. There's some question you need this. Okay. Now I can actually change it, knowing that omega is equal to 2 pi f, and of course phi is equal to kx. All right. So I can change. So this can also be given as y is equal to a. All right. Sine open bracket omega is 2 pi f, so I can change it now to 2 pi ft, then minus, right, kx. This is already k, wave number, so wave number multiplied by x. Okay, wave number, which is 2 pi x all over wavelength, of course. So you can call this 2. So let's look at 1 and 2. Take note of it. Okay. All right. Of course, I will apply that now so that it will be clear. Just, I'm only interested in showing you how you can use this to answer questions. So I'm gonna pick up a question now, which of course we are gonna apply to illustrate what we have. All right. So here we go. Okay. I bring it to the board. Right, here we are. So the question goes like this. I hope you can see it. Okay. The equation of a wave traveling along a positive x direction is given by, so according to the question, the wave equation is given as y is equal to 0.25 times 10 raised to the power of minus 3. All right. The sine open bracket 500t minus 0.025x. Okay, so what I'm looking for, the question says determine the angular frequency. So this question wants us to find omega. So how do we go about this? Okay, we'll compare this equation to the two. I gave you two equations, all right? So I'm going to compare it. I'm going to compare it with one that has omega in it, and that is the very first equation. Okay. Okay. Hope you've not forgotten it. Y is equal to a sine, all right? Open bracket omega t, all right? Of course, minus phase angle, right? I just use this, right? All right, shall we go? So comparing this, now discover that 500t omega t. So the angular frequency, comparing it with this, because it's the angular frequency is the coefficient of the time, and of course the coefficient of the time in that wave is 500. So that's 500, of course, is measured in rad per seconds. But let's say a situation where this question was find the frequency. Sorry, find the frequency. Okay, not the angular frequency, but the frequency of the wave. You know what happens now? So that simply means that, okay, see omega. Remember the omega here now, it is 2 pi f. The omega represents 2 pi f, right? You know that already. 2 pi f. Okay, and of course 2 pi f is going to be equal to 500. Right? So it is easy now for you to now get the frequency. That's frequency now becomes 500, okay, divided by 2 pi. I'm just showing you exactly how to, this exactly how you actually work with equation of a wave. Let's say the question is now also a situation where you're being asked to evaluate the wavelength. Simple. You use this wave number, okay, the one that has a wave number. Of course, the one that has a wave number, the whole of this, okay. Remember, it is 2 pi wave number divided by lambda, okay. x. You compare it to this, okay? The coefficient, if you equate it to the coefficient of the wave number, this becomes the wave number, okay? This becomes the wave number, right? This becomes the k. The k becomes 0.025, right? And we know that wave number is already 2 pi all over lambda, okay? So which is 0.025, okay? So just for you to rearrange this equation, and of course you're good to go. So it's just simple way of working with equation of a wave. All right, so now that is it. Let's see if we got another question now, so that we'll make it clear, right? I get another question. Here we go. I hope I'm not running too fast. Okay, I have a question here now. I'm gonna bring it to the screen. Okay, here we go. Okay, should I? Whether it will be seen. Better still, let it be. Okay, so I hope you can see it. So given the progressive wave equation, this time around, the wave equation is giving us y equal to 5 sine 200. Okay, 2000, right? 2000 pi t minus 0.4x. Right, so the question is find the wavelength. Of course, the wavelength we got it from the wave number. The wave number there is 0.4, right? Which we know that the wave number is 2 pi all over lambda. That's where we get the wavelength, right? Okay, which is 0.4. Of course, cross multiplying, we have 2 pi equal to 0.4 lambda, right? So lambda now is going to be equal to 2 pi, right? Divided by 0.4. So you can use your calculator to do this. Of course, this should give me, that should be 5, right? Yeah, you can just use a calculator. 5 pi 2 divided by 0.4 should be 5, if I'm not mistaken. So 5 pi meter. Of course, if the answer is not in terms of pi, you can actually put the value of pi. Pi is 22 all over 7, right? And of course 22 all over 7 is 3.14. Okay, so that is just it. I'm giving you, okay, a very good approach to solving question that deals with wave equation. All right, so we can proceed. Excuse me. So we're gonna be talking about, I think that should be the last part. All right, we're looking at basic concepts, and of course, so we're gonna be talking about the characteristics of a wave. Okay, characteristics of a wave. Every wave have the following characteristics, we should know. Okay, no matter what wave, okay, it is sound, light, okay, they have these following characteristics. Okay, wave have the following characteristics. So a wave have the characteristics of reflection. Every wave can reflect. Every wave can undergo refraction. Every wave can undergo diffraction. Every wave can undergo interference, and every wave can undergo polarization. Okay, so that is, I mean by every wave types, okay, or yeah, types of wave. All right, but there are classes of wave that doesn't undergo some of these characters. For example, okay, polarization can never take place in a longitudinal wave. Okay, so please take note of that. Polarization can never take place in a longitudinal wave. So there are some classes, okay, that doesn't undergo some of this. Okay, but rather a polarization only occurs in a transverse wave. So let's start talking about them. Reflection, of course, as the name implies, okay? Reflection is the bouncing back of wave, okay, back to the medium as it encounters an obstacle. Let's say this is a boundary. We talked about reflection, okay? A wave comes to this boundary, hits this boundary, then returns back, right? So I can use a line. Let's say I'm considering ray now. Let me use a line to make it easier, okay? Let's say I'm considering a ray of light, okay? A ray of light hits a boundary, because light is also a wave, okay? Then it reflect back. That is reflection, okay? So please take note of that. Take note of that. All right. So that's reflection. Please then we'll now let's talk about refraction. Refraction. I hope you're writing this down, okay? Now refraction is a process where a wave changes directions, okay? Changes direction as it moves from one medium to another, okay? And of course, two different mediums have different densities, all right? Let's say I have two medium, all right? This, pardon me. I have two medium. One medium is air. Let's say inside here is water, okay? Then this outside is air. Light is moving. Light is moving in a straight line, okay? As it enters this medium, okay, it bends, it changes direction, okay, or it bends. It's still something changing direction or bend, okay, it bends. So we are simply say that this wave have actually refracted. Why is it that a wave moves from one medium to another? Why does it refract? Why does it bend? Okay, why? Because the two medium have different densities, and that different density will give that wave, okay, different velocity. So it simply means that in air, this wave have velocity v1, and of course in the water it has velocity v2. So definitely to actually bend, and of course the change in density will also affect uh, the the wavelength. Velocity will change, of course the wavelength changes also. So in air, let's call it lambda 1, of course in the medium lambda 2. So anytime wave move from one medium to another, okay, the velocity and the wavelength changes. Please take note, what can never change is the frequency. Frequency remains the same, because frequency is just vibration, okay? It has nothing to do with of course length or whatever. All right, it has nothing to do with linear distance or whatsoever, okay? But velocity and of course wavelength have something to do with linear distance, but frequency doesn't have anything to do with linear distance. So its vibration still remain the same in the two medium, all right? So please take note of that. So that is refraction. Then diffraction. Now diffraction is the spreading, okay, of a wave, the spreading of a wave as it actually passes through a minute aperture or minute opening. All right, a wave passes through a minute aperture, it spreads out. For example, let's look at this is a small, this is not a boundary but a small aperture, okay? A small aperture, small tiny opening, and I have a wave, okay? A wave, as it enters, passes through this, as it passes, it spreads out, okay? So that is the reason why someone stay in a room and actually talk, okay, from a window, a tiny opening, someone outside will hear, because as the sound passes through the tiny opening, all right, it spreads out and someone outside will hear. And that is the same mechanism that loudspeakers actually uses. That's why you see loudspeakers, okay, actually have this shape. So as sound enters inside it, okay, it actually spreads out. All right, so please take note of that. That is diffraction, right? Then of course we talk about interference, of course, as the name implies, okay? Wave, if we have different wave traveling in a medium at the same time, different wave, okay, in the same medium, all right, there's this tendency that they will interfere each other, okay? So interference is simply the overlapping of wave that have, okay, identical wave that have nearly the same frequency, mostly what overlapping wave that have the same frequency, okay, or perhaps nearly the same frequency, that the difference in their difference is not much. It has the ability to overlap, right? They will overlap each other. In fact, this particular characteristics of wave is mostly, it can be noted very much, okay, noticeable in electromagnetic wave, especially in radio wave. If you notice what happens most of the times, you tune to a radio station, and in the background of that radio station, you hear another sound, okay, which is from another radio station. So it simply means that those two radio stations is probably transmitting almost at the same frequency. All right. So they overlap, and once you tune to that frequency, you pick the two because they're overlapping each other. Now let's actually use a graph to describe interference. Okay, so I want to describe it with a graph. Let's say you got this, and of course interference, okay, can be constructive. So I'm talking about a constructive interference. A constructive interference is such interference, okay, it's an interference in which the wave add up to form to have to give their sum, okay, they add up themselves. And of course, for a wave to have a constructive interference, they must be, okay, of the same phase. Let's say I have this wave, okay, wave 1. That's wave A. Okay, let's say then I have wave B, probably of a smaller amplitude. Okay, so when these two waves overlap, the result you will have is, okay, superimposing on the bigger one. All right, something of this nature. So in constructive interference, it's called that two of them are, since they are of the same phase angle, okay, their crest will always coincide. The crest of one will coincide with the crest of the other. Okay, their crest coincide at the same time, so that's why they will add up. All right, their crest coincide with their crest, their trough coincide with the trough of one coincide with the trough of the other, and the crest of one coincide with the crest of the other. Because they are of the same phase. But if these two waves are out of phase, they might end up cancelling out. Okay, let's see a situation where they're 180 degrees out of phase. And of course, 180 degrees out of phase simply means that one is positive and the other one is negative. Let's say have something like this with A. All right, so coming to interfere with B, and B is negative, the same frequency, but okay, out of phase. If these two interfere, all right, the result you get is this. Okay, the result you have is a stationary wave, something that looks like a stationary wave. Okay, one is positive, the other one is negative. Okay, they will cancel out. Of course, and at that point you may not have any effect. So whenever a wave interfere, let's say in form of radio station, one radio station is transmitting in a particular frequency, another one is transmitting same frequency, but they're out of phase, they can cancel out, and you pick up nothing. All right, you will not hear any sound. That is just how that works. All right, so that is it for interference. Then the last but not the least, we talk about polarization. All right, polarization is the process of making a wave, okay, that have different plane of vibration to only vibrate in one plane. Let's say a wave have different plane. In fact, let's say the plane of vibration is different phase. A wave that have different phase of vibration, okay. A wave can have different, especially lights, specifically lights, okay. So, and of course, if you move in the medium, that's how it will carry different phase, okay, of its vibration. So if I could pass it through a device known as a polarizer or a polaroid, okay, what happens? The polaroid actually, what it does is that it cancels all the plane and allow one plane, okay? So a polarizer is actually created such a way that you only allow one plane of vibration or a ray that has one plane of vibration then to pass through it. So at this point now it cancels every other one, and allow one. So at this, once the one that passes through it is said to be plane polarized because it's is vibrating in just one plane that the polarizer allow. So we can simply say that if a light rays of high intensity passes through a polarizer, it will reduce its intensity. Okay, why? Because some of the rays have been filtered. So a polarizer acts as a filter. Okay, filter of rays of different plane and allow one of a particular plane to pass through it. And please take note of this, is only transverse wave, okay? Transverse wave that undergo polarizing, because it's only transverse wave that we know that, all right, the medium and the wave are actually vibrating perpendicular. So it's only transverse wave that undergoes polarization. Right, so these are just basic terms, okay? I just want to give you the basic term of in as much as wave is concerned, because that we can use to solve questions. All right, so we are gonna solve questions definitely in a moment. All right, so let me give you a break. All right, so in a moment we solve questions. All right, thank you.